Everybody, and thank you for letting me be your post-lunch nap. We have something pretty exciting, I think, that we've got a lot of people talking about, and I found people get pretty animated about this topic, so we'll have some fun. I've been talking about and automating infrastructure for quite a long time, since very early cloud infrastructure days. I've done a lot of work with open ops. My company runs an open infrastructure project called Digital Rebar. I help co-chair the cluster ops SIG for Kubernetes, where we actually try and talk about operators and operations issues. I was on the OpenStack board, and I actually wrote one of the first OpenStack installers way back in the day called something called Crowbar, which this crowd may or may not even remember at this point. So this story starts for us at a self-bootstrapping Kubernetes deployment that we built. So we had this idea for KubeCon to be able to do a demo where you would roll out a rack of servers, turn them on, and lights would blink and Kubernetes would self-install at the end of the day. So completely automated Kubernetes. Using immutable boot, which would mean an in-memory boot image, like using Container Linux or something like that. That would install Docker, find a leader, run kubeadm or kubeatom on the server to do the install process, so the open source installer, and then run kubeadmin to join all the nodes together. So basically, automatically wire up a Kubernetes cluster. And we built it. It's pretty cool. There's a video link in the next slide. But what we found was that demo, which was super easy to sort of build and do, was also very hard to maintain, because if Docker, heaven forbid, Docker would change a rev, or kubeadmin would change its sources, or anything would change, wiring all those things together would break. And so that wiring effect, even though the infrastructure was immutably booted, in-memory booted, it didn't work that well. And so that made us, the thing worked pretty well. We didn't want to have to keep maintaining it and tweaking it and keeping up with all the changes. And so we were pretty sad about that. Definitely something to check out. It's a really fun demo. I think I'm actually giving it tomorrow at the Kubernetes community meetup also. So you can see it a second time. It takes about 5-10 minutes to do. But that's not the topic for today. The topic for today is how do we fix that problem, right? Why is this type of configuration very fragile? And the reason it's fragile is because we're talking about mutation of a system. And so mutation is change. So anytime we're taking configuring a system, we're really changing the system. That's the whole point. But as we make changes to things, we make it more and more fragile. And what's happening is, even if we have a system using a DevOps tool, Chef, Puppet, Ansible, Salt, I heard somebody shout out the CF Engine, the Rundeck's here in force. If you're using one of these tools, you're building an infrastructure as code topology, you are also creating a problem where you're building everything in the wild, in the field. You're actually working to make it built in place. And so if you have a fleet of a lot of servers, a lot of virtual machines, in that fleet, every one of those systems has to be configured and managed, and then that creates a dependency graph. So the Kubernetes example that I'm giving had a dependency problem. Because Kubernetes, running that one single install Kubernetes command actually required us to have done a whole bunch of things right first. So that graph would cause issues. If there was variation between environments, that would be a problem. And so it was very hard to lock down that system because we had to do we had to have root access to do that configuration after the fact. So there's all these this is really cool, I can automatically provision things, but there's a huge but that comes from that. And then it was even harder when we would try to do updates and patches. So when I was in the OpenStack community, we were always looking for the self-upgrading OpenStack environment. And that, making that work in an environment is really, really hard, because as soon as you've installed it, things get into this indeterminate state, and then your upgrades and patches fail. And so the answer is to lock all this stuff down and say, well, wait a second, what if we don't have to patch our systems? And everybody knows that's not a feasible alternative, right? The world's changing way too fast to not patch it. So we need a different alternative that involves not changing systems and changing systems at the same time. And that's what immutable infrastructure is really about. And if you don't like the word immutable, I talk to a lot of people who don't like that word. It's either got too many syllables or it just sounds weird to them. Whatever your objection is, what we're really talking about is pre-configured systems. They're pre-deploy configured systems. So if you're used to the Docker world and the container world, you go to do a Docker build, you put that in the Docker hub, or wherever you're caching your Docker images, and then you pull down that image, it's all there, right? You're not running apt-get install or apt-get update as your first action when you start that container. Hopefully you did it during build time. And so it looks like this. This is the traditional model, and I want to keep looping you through this. So I'm going to try and reinforce this point, hopefully make it very, very clear how we're talking about changing configuration and configuration management. So in this graph, this is your traditional graph. We code, we build, we integrate, we do all our testing, we go to deploy our code, that's great. Then we have to configure a whole bunch of servers to have that image and that code and all the dependencies, and then we run them. Sounds pretty good. What we really want to be able to do is do that configuration before deployment as part of our build process. So in that case, we're actually building a single artifact that has all of the pieces and parts that we need integrated, tested, everything looks good. So when we go to deploy, we're actually deploying something where we know all those pieces work. We're not resolving a dependency graph and doing an install and did something change? Did somebody remove shift left from my JavaScript library and break everything? Right? We want to get that done before we hit deployment. And it's not practical to do all of your deployment, all of your configuration, one image per machine. So what we really talk about doing here is we build a general image that has all our pieces. We deploy that general, and then we do some post-configuration. So we're not talking about completely immutable. What we're talking about is I deploy something, I run some post-configuration. Typically, people know cloud init is the way you do this. It's not the only way to do this, but that's the dominant in cloud pattern. You cloud init, so you do enough to get the system running, and then you run the system. Okay. If you really want to go to the next step further, I highly recommend Justin Garrison and Chris Nova wrote a book called Cloud Native Infrastructure. That book takes this concept to another level. That other level says, oh, wait a second, if I have these immutable units, I can then put a state manager around it, and then that will then do all this magic for me. And that ends up being a Kubernetes conversation, and this isn't a Kubernetes talk. So we're sort of going to get to the, wow, I can do all these cool stuff. I want to get you to the point where we have these immutable artifacts and you understand why they're worth building, and then you can get into making them do more and more dynamic tricks and jumps and things like that. Fundamentally, immutable is a DevOps pattern. So what we're really talking about is a pipeline, lean inventory type of thing. That's when I think of DevOps. It's about a process and a pattern and inventory management. And so what we're really trying to do from that perspective is shift configuration to the left of our pipeline. If you haven't been hearing the term shift left, I strongly recommend doing some research in this. It's in security and things like that. What we're really trying to do is move actions that typically happen in production into build pipeline. And that means that we can do security scans and vulnerability analysis and certification, all sorts of actions before deployment when it's a very controlled environment and it's very safe and repeatable. An earlier talk today, in one of the keynotes, one of the plenary sessions, was talking about rollback as an important value. And so the idea here is if we're building something as an artifact, we can move it backwards and move back to something we've built in the past. So that shift left is a big part of it. The other thing that gets enabled here is this create, delete pattern. So if you're used to physical infrastructure, we really focus on the physical side, but people make this mistake in virtual machines also. If you treat the machine as a long-lived machine, then you can be very much in the habit of saying, well, I'm going to patch it, I'm going to update it. Cloud enables you to have this pattern where you destroy machines and then you build new ones. So it's this create, destroy pattern. So if you're doing this pattern, it doesn't mean you're immutable, but you're certainly a lot closer to an immutable deployment than anything else. So this is what we solve by looking at an immutability pattern. And this will illustrate the shifting left concept. So we build a server, we provision our server, we do our configuration. In normal operations, about 30 seconds after you've done that deployment, you're going to get a patch. You're going to take that patch, you're going to rerun your configuration system, and apply that patch to the live system. A minute after that, you're going to have another patch, and that patch is going to have to be applied into the system. And you're going to go into a madness zone, right, where we keep going through and trying on the treadmill of patching this system. Every time you apply a patch, your ability to know the state of that system decreases, right? And so, because something could have happened, the patch might not have taken. It could be that things were happening out of sequence, and building an immutable DevOps toolchain where you can continue to run the same script on the same machines and have them not have strange results is very, very difficult. Not impossible. I haven't met anybody who does it, but it doesn't mean it's impossible. So what we really want to do is stop this madness, right? We want to say, look, I don't want to have to maintain root access where I'm always patching. That's a vulnerability. I don't want to have to rely on the fact that I can download a patch to make something work. I don't want to have to coordinate activities between multiple machines while I apply a patch. So if you have more than one machine, if you're applying a patch across multiple machines, you might probably need to coordinate. I'm not changing my database server on every machine at the same time. I'm rolling that change through. I'm making sure it's stuck. So that you have to do all that work. So this pattern makes me sad. I've lived with it for a long time. I've been in a lot of firefights where we had to figure out what was going on with our configuration drift and things like that. And then our only choice was to add more configuration drift to try and fix the configuration drift. And so that becomes a very, very sad chaos spiral. So the solution is to approach this differently and say we do not want to have this ongoing patch configuration battle, this mutability in our system. So what instead we want to do is we're going to go through this initial server. We're going to go through the provisioning process. Now we're moving the patch to the left. So now we put the patch in, we build the system, and then when we get to the end, we re-provision a new system with the new configuration. Sound good? Then we destroy that system, we bring in a new system. So in this case, we're taking advantage of this create-destroy pattern. If you can get to this pattern, you're stressing your build system, but what you're doing is you're creating a much more repeatable deployment result, which is really what our goal is. And then ad nauseum, you're going to keep this pattern going. And this is very cloud-like behavior. So if you're in this pattern, it's very cheap to create, destroy machines. As a matter of fact, it's a very good budget model to be able to say, all right, I'm going to destroy a whole bunch of machines, I'm going to create new ones, right? One of the things that Netflix was famous for doing was they'd spin up excess capacity, they'd performance test everything, and then crush the machines that weren't performing as well. And they would use that as a benchmarking system so that they would get the good machines, not the bad machines. Right. And this allows you to have that type of very, very performant behavior. And when we say cloud-like, it looks sort of like this. It's a black box. We say, I need a machine in this state. Give me a machine in this state. Go build it. Do all that work and exit. In reality, and this is as SREs to me where we need to put our hats on for this pattern. In reality, there's a lot of black magic that's going on in this case. So if I'm requesting a state out of the system, I'm going to come in, I have to reset a machine, I have to initialize it, configure it, test it, I have to join it to a cluster. So there's a lot of work that has to go in. And as an operator, as an SRE, we don't want any hidden operations in our infrastructure. So if I'm trying to troubleshoot an immutable infrastructure, yes, I want to give you an image, I want it deployed at the end. And a lot of the developers or the pipelines might say, that's all I need, I'm done. As somebody actually managing this underlying platform, we don't want hidden operations. So that same benefit that you get with a cloud abstraction barrier causes problems. And it's not bad. Matter of fact, I would say it's required to ask for a high degree of transparency in operations so that as things go through this pipeline, you need to know it. Because we're talking about infrastructure that's much more dynamic. So if your create-destroy pattern has weird, flaky behavior, this will not work. You have to have very reliable create-destroy patterns for this type of system to work. So if you're dealing with a cloud provider where you ask for an instance and you don't get one back, or you occasionally get one back, or you get a broken one back, you're going to have to build more defensive capabilities into your system to do this, and you're going to be tempted to drift back into a I've got a machine, it works, don't touch it, leave it there, right? That's what we used to deal with in cloud quite a bit. So there's a couple of patterns. So we've sort of laid out the problems as the whys. I want to go through some of the ways that we see immutability being implemented, because there isn't one right or wrong way to do immutability. I'm not a fan of immutability shaming people for doing it one way and not another. So let's lay out some actual practical patterns that you can implement. The simplest of these, sort of the starting point, is baselining and plus configuration. So if you've already got infrastructure as code, you're already doing post-boot configuration, and somebody can bring you a fresh machine or a fresh VM, and you're like, oh, that's no problem. I know exactly what to do. I'll run the script and I'm done. This is what that would look like with the addition of a reset. So the idea here is that we're going to be able to just go through our normal process. We're going to run the machine, ran our scripts, everything was good. Instead of going and patching, what we're going to do is reset the machine. So we're going to take it, we're going to tear it down, clean up the disks, and then make it available again. So this is a really interesting pattern. This is basically, it's very close to what we were talking about with the Kubernetes demo. The challenge with this is it's pretty slow. So what you've got going on here is you've got high degree of hygiene out of the system because you're building pristine every time. You still have to resolve a dependency graph on that setup. You still have to go through the full configuration process. So this is a good first step, and it's a perfectly legitimate way to do immutability. The Kubernetes demo I was talking about is a step further, where some people don't want to have to go through the process of resetting an operating system. And what they'll do is they'll skip a step of installing an operating system and do an in-memory image. And you don't have to use CoreOS to do this. You can do in-memory live boot on any material operating system will support this behavior. And the idea here is that now you go through the same process. You install in memory, which is faster. You can attach your disks and do the deployment, and then run the systems. And then when you're done, or when you're in a refresh cycle, you just reboot the machine, and then everything goes away. So if you were in a place where you were very worried about attackers compromising your systems, or people doing manual configuration on a system that you didn't think they should be able to do, in this case, you're one power cycle away from wiping out everything somebody did on that system. Okay? And it's a little bit faster because you're not actually reinstalling the operating system. You're just reconfiguring the system. This is exactly what our Kubernetes demo did. There's one gotcha with this that people need to be very, very careful of. Your boot infrastructure, boot provision infrastructure, becomes critical path infrastructure. Very few people I know have real HA, DHCP infrastructure, because it's super hard to do. They're not prepared to have machines rebooting randomly all through their days, or if there's a power blip, all the machines come back online at once through a boot provision system. And so while this is a really exciting pattern, people in the Kubernetes community get really excited about this CoreOS and everything, minimal configuration, no SSH capability. It puts stress on an infrastructure that you have to be very aware that you're putting on the infrastructure. Not a bad pattern. And then this is the pattern that we've seen people getting really excited about adopting. In this case, this is an image deploy pattern. So what happens here is that instead of using normal configuration management tools in deployment, you build an image, a lot of times with configuration management tools, in your pipeline. You get a pristine image, and we'll talk about some of the ways to build that. And then that image becomes what you deploy. This is what we'll show on the demo. And that image is literally written to disk. You boot the machine, all the configuration, or most of the configuration is done, and you can simply run it. It's more work to create those images up front than you've done in the past with Chef, Puppet, Ansible, Salt, whatever. But once you've done it, it's very easy to get that pipeline going and actually build a very good system. It's important to remember you're still doing initialization. So you don't just take random images, dump them on disks, and you don't build one image per instance you're trying to build. You have to have a post-configuration system that you track. So you still are managing inventory, you're still managing machine personalities, you're still tracking your overall system, but your amount of configuration is decreased dramatically. And your time for configuration is decreased. So I'm not dragging bits down for every machine. I'm not running an installer for everything. I've packaged an image that has everything in it. And the results, I was pretty skeptical about this when I first started hearing this pattern. The results that you get into from a pattern like this are, for what we're measuring, is a 5 times improvement compared to normal net boot activity. Okay, so I want to be very specific here. So if you're in a situation where you're pushing out new builds of your software and you want to do that as an integrated unit, if you can improve the time it takes to reset your system by 5, then you have dramatically improved the amount of capacity you have available, and you've reduced your downtime windows on individual machines going through the system. So it's a very significant improvement in performance for this. It does have the challenge of having to think through what image creation means for you. So image creation does not happen magically, right? You still have to do the configuration on a live system somewhere. You're still building that image up. It can be completely automated. It can be put in pipelines to do it, but there's no free lunch. You're still configuring the system. The win here is that you're configuring the system in your pipeline, where you're doing it really one time for your whole fleet, or you're doing it one time for that application. And then you're not repeating that process in production where it's more flaky or less stable, or you don't want to take the risk of troubleshooting. Oh, wait, this dependency that I thought was available on the internet, or I thought I had the right cache for, the developer changed the reference to, and I don't have the cache, and now my systems don't build correctly. So, right, we're talking about having to do more work up front. And there's tools that make this very possible to do it, and they're just, at the end of the day, they're just raw disk artifacts. Some people ask me about, does this create a huge storage burden? You do end up with images in your inventory, but we're not advocating creating, you don't have to keep every copy of every image that your system produces. What you're going to do is, just like any versioning, you're going to have a whole bunch of intermediate steps. You might deploy those through your system and then destroy them afterwards, where you keep good known stable points. So you might snapshot a release or a known good point for rollback, and you might keep a week's worth of images in case you needed to fall back. And one of the big benefits here is that it really is a way to implement rollback. I don't, other people have been more eloquent than me about why rollback is important. What we're really trying to say is, look, I want to be able to go backwards in time to a pre-existing system. It's almost impossible to do with a configured system. It's hard to unconfigure something once you've added or made a change. But with this pattern, I can literally say, oh, that deployment doesn't look so good. I think you introduced a bug. Let me stop the deployment with this image, roll back to a known good image. And so it really gives me the ability to come back to a verified, known good state, and then repeat that state across my infrastructure. And it doesn't matter if you're talking about containers. It doesn't matter if you're talking about VMs or physical machines. It's the same pattern. And to me, one of the things that's really exciting here is that this is a place where, with immutability, developers and operators and SREs are getting very aligned. Right? We're understanding containerized deployments and how fast we can roll containers. This is taking that exact same prototype, that exact same working pattern, and then applying it into more general operational patterns. Right? This is why that Kubernetes book I was talking about gets super exciting, because in a lot of ways what we're talking about and showing with Kubernetes and the way we can handle rollouts and application and service deployments, we can actually use those same techniques across our infrastructure. They don't have to be limited to one platform. And so it's a big deal, right? We actually are creating a more manageable, faster, and more scalable type of deployment with this process than you might be used to. Okay. I know when I first saw it, I was a little skeptical about the work involved, but the speed, performance, and reliability is very powerful. Okay. So I've got 15 minutes left. My plan is to leave about 5 minutes for questions. If you've got a burning question, stand up and come to the mic, and we'll take a burning question. Otherwise, I have a demo. It takes about 5 minutes to run through, and I was going to sort of queue up the demo as a thing. So. So here's the demo. And the demo's sort of hard to visualize all the pieces, so I'm going to show you in pictures first, and then we'll do it. So we've pre-created an image. So we took a reference system, we ran a script that basically pulled that machine image out, stored it as a raw file, as a tar, effectively, right? If you're going to Amazon or an AMI or a disk image or a VHD, it doesn't really matter. In some cases, if you're going like to like, you can just rip a whole VHD and move it. There's a little bit more magic that you can do in these configuration systems than just that. And then what we're going to do is we're going to take that image, we're going to go into our deploy phase, so we're going to boot a system, and this is where it gets really important. I don't have the image to boot from yet, so I have to run an in-memory system, so I can take that image, I can copy it to my disks, I can fix the boot partitions for the disks, so I'm going to write it into the system while I'm in memory. Then I can reboot that image. That image has now been deployed to disk, and I can boot it. So now, at that point, the target system with that image becomes the running target system. And I always like to re-emphasize this, and I'm not done. I have to go in and then do some cloud initialization, or I have to run an agent or something like that to initialize it. Just putting a chef agent on it or a puppet agent on it and having it phone home is not sufficient because the machine's identity hasn't been reset. So you do have to do a certain degree. There's probably some DNS, DHCP tricks you could do, but by and large, you need to remember that you're going to have a post-configuration stage of that. Okay, so that's what I'm going to show you in the demo. The demo. The demo uses, this is the UX we build on top of an open source project called Digital Rebar. So I'm going to walk you through what that does. But fundamentally, what I have here is I have a virtual machine. This is entirely running on my laptop, so there is no internet dependency in the system. And what I'm going to do is reset it a little bit. So I have the VM running. I'm going to go and reset this system back into a reset state. So what's happening, actually I'll pause. So the VM's going to reboot in the background. It's going to reset it to make sure everything's clean. What this will do is it's going to implement a workflow. It's going to implement this workflow. So what happens down here, it's going to be hard to see from the back, I'm sorry. But basically, when machines are first discovered, they go through a process that gets them prepared to be run in this infrastructure. So they go into basically an in-memory boot. For us, it's based on CentOS. You could do this a number of ways. And then it goes into a waiting state where the agent's just waiting for instructions. What I'm going to do is I'm going to move it into a deployment workflow where I actually go in and take the image, deploy the image. That will take it through the first part of the process of copying the disks. Then when it reboots, it will go through a cloud init process and then mark itself complete. One thing that's important with this, especially if you're doing Windows in this process, which is very fast compared to a traditional Windows install, is you need to be able to know when things complete. So it might take 2 reboots to finish preparing a system. You're still installing an operating system. And so you do want to have some way to hand off so something goes up and says, hey, the system's done installing, and you can put it back through its workflow systems. Okay? You can get false positives if you assume your first reboot is your only reboot. If you're deploying Windows, you're up for multiple reboots anyway. This isn't something unique to this environment. It's the way Windows installs work. Okay, so if I check back in on our system over here, it's gone back through the system, and it's in that wait state. Remember, at the end of the workflow, it gets into a wait state. To move it into a Linux deployment, what I could do is I could simply start the workflow. I could simply set it to the beginning of that new workflow, which would be an image deploy. The thing I would say is that the point here is not to do this on a UX. This is supposed to be an automated system. So I'm going to show you a CLI initiating this command instead. So in this case, this is just going to update. It's going to do the same thing as would do by clicking buttons. But here, what I'm going to do is change that stage to the start of that workflow. And it's going to go through the process and start doing the install. So in this case, it's going in, and it's started that install workflow process going. And what I can do is I can actually jump in. And in this case, we're downloading an image. The Linux images compress very nicely, so they're small. It's about a 10-minute process on this laptop for the Windows to transfer from my SSD to my SSD, but it's a big image. And so once the system's finished downloading this infrastructure, it will go through an automatic reboot. We're actually doing it right now. And then it'll complete the process. And I can show you, I should have shown you the machine. So this is actually the reboot of the system going through, and it's going to go and finish the initialization stage for the system. I'm going to jump back over here. And so it actually just finished. So if you're used to net booting Linux, right, in the last 3 minutes, I literally did a complete system reboot, drive to disk, install Linux, and have Linux up and running inside of that 3-minute window on this laptop. Normally, if I'd done a normal netboot install for CentOS, it's about a 9-minute process. And that doesn't include any post-configuration that I might have added. So if I wanted to then install Kubernetes or install something else on it, one, I would have been relying on conference internet. And two, I would have been actually going through an install process where Docker figured out what was on the operating system and triple checked that it had all those things, all that work. So if I was to do this and install Kubernetes as part of this process, it would take me probably 15 or 20 minutes to go through that whole process. By putting it all together in one image, I actually can eliminate all those steps. And that's actually, there's another step we're about to do in this demo that I'm not doing today, but where we actually bake all the Kubernetes pieces, Docker pieces, Kubernetes pieces, the images into that, and then you're transferring it, and the system will boot just about as fast as this process. So you're just waiting for the Kubernetes initialization to come up, not the install process. Cool. That actually only took 8 minutes to do the whole demo. So I have time for questions. Do I have people questions on the process? No? How many people are using a process like this in their current infrastructure? Oh, yeah, it's about 10% of the crowd. How many people are looking at doing something like this as far as what they're doing? Okay, so it's about 20. And how many people feel like if they have, how many people don't provision servers at all? Okay, I was going to ask why you came to this talk. So how many people have a process where they can reliably bring a server up with zero touch from scripts? Come on, everybody in the room should be up. Wow, goodness. So about half the room has some reliable way to bring systems up. I mean, really, get that. That's important. The nice thing, one of the nice things about doing this process is that if you can automate and reliably bring systems up over and over again in your build pipeline, then you're going to be a lot more confident about what's going on. If you're the person who's chasing around, hey, I have a server in a colo or in a cloud somewhere, and I'm SSHing in to find out why my script didn't run correctly and what broke, move that into your build pipeline. Move that pre-deployment, because I can tell you, because we've done this for a long, long time, it breaks every day. Every single day, somebody removes a dependency graph, right? Ubuntu decides that they're not going to support this, they're going to take their latest patch off a mirror somewhere, and the image you were relying on isn't there, or somebody's dependencies changed. What we found was that every single day, something broke in our dependency graphs, which meant that if we went back in time and tried to deploy something from 2 months ago, the likelihood of it working would asymptotically approach zero very quickly. And that's bad, right? If somebody calls me up and says, you know, I deployed this software and I can't recreate the build, and I can't go in and fix it because my dependencies have messed up, then we're going to spend a lot of time either telling whoever had that to upgrade and patch, which to me is a sad conversation, or we're going to be back in trying to troubleshoot, do things one-off, and that's not a good pattern either. It would be much nicer if I can come back and say, let's just go back to the image we had 2 months ago. Yeah?
I've got a question. Hello? Yeah. How does immutable infrastructure apply to stateful bare metal servers?
So the question is about stateful bare metal. There's a couple of approaches that you can use to do stateful bare metal. One of them is to treat the disks in the system separately from the operating system disks. So most people doing a bare metal deployment already separate their data disks from their operating system disks. And so in those cases, you can treat the operating system as immutable and apply these techniques to it, and the data in your infrastructure as static. So you have to have more intelligence in that process. In the deployment systems to know that you're putting a system back in the same place so that you're not moving data around. Or what you're doing is you're actually going to say, all right, I have a replication strategy, so my stateful app, the data is distributed and replicated in case a server fails. So ideally, you're like, oh, my servers already replicate data across multiple systems, so there's redundancy. And if I took one out and patched it, nobody would care. Hopefully that's your case. If you're not in that case, then it's going to require a little bit more work to fix it. And I would say fix the fundamental problem, which is that you don't have good resiliency in your stateful app spread across multiple servers. And that, because here, the wonderful thing about immutability, and I didn't mention this in the talk, is if you're building infrastructure, it will fail. And if you can't handle somebody destroying a server and it being completely gone in your infrastructure, then you have a very serious operational contingency problem. You need to fix that. And in fixing that, you will also be making yourself ready to do this type of immutable infrastructure piece. And so there's a hygiene question in that I think by addressing the hygiene problems, you can make it easier. It's totally possible to do stateful applications for this pattern. I'll give you a big but on that, but start with the stateless ones. So that the stateful ones get the process all working on the stateless things, and then work it in stateful stuff. So yeah, that's probably the biggest takeaway is start on the low-hanging fruit for immutability. Cool, great question, thank you. And with that, unless there's another question. Cool. If you're interested in more details, this is what we do every day, so we love to talk about it. And we have a booth outside, and we'll happily go through the demo in more details and things like that. So, thank you very much.